How are you with lifts? Personally, I hate them. It doesn't matter how big or pleasant the lift is, I will always avoid them and where possible, use the stairs. If there are people in there, well, that's even worse. My nightmare would be for the lift to break and go into free fall. The physicist in me starts to calculate the forces involved and what would happen if I suddenly started accelerating downwards in a small metal box. Trust me, the outcome is not pretty. Do you want to know how it might go down? Let's find out. This is Think 4. Understanding how you would fare in a falling lift requires me to consider your weight, or more accurately, your apparent weight. When you stand on the scales in your bathroom, your weight acts downwards on the scale. Mass multiplied by gravitational field strength. There is also a normal force acting upwards, the reaction force of the scale pushing back on you. This force must be there as you are standing still. There is no unbalanced force acting. Newton's first law tells us this. The reaction force is actually the force that is shown on the scales. So if the reaction force acting on a body were to change, the reading on the scale would also change. If the lift is accelerating down, there is now a smaller force acting upwards on you compared to your weight acting down. The reaction force is now smaller. Therefore, the reading on the scales actually decreases. Your weight appears to decrease. This is your apparent weight. If the lift is accelerating upwards, well then, the two forces change as well. In this scenario, the reaction force acting upwards is increasing as the lift accelerates upwards. The force is greater than your weight acting down. This means your apparent weight will be larger than before. Remember, if the forces are balanced, your apparent weight and the reading on the scales will be the same as if you were standing still in your bathroom. So, if the lift was moving at a constant speed, the forces would be balanced, and therefore the resultant force would be zero. The reaction force acting upwards would equal your weight acting down, and the scale would read your weight. The type of question that you could be asked may go something like this. A person stands on a weighing machine in a lift. When the lift is at rest, the reading on the weighing machine is 700 newtons. The lift now descends and its speed increases at a constant rate. So what happens to the reading on the scale? Let's highlight these things. At rest, the reading is 700 newtons. So when the forces are balanced, the weight is 700. The speed increases at a constant rate. This means the acceleration is constant, and therefore the unbalanced force is not changing. As the lift is accelerating downwards, the force down must be bigger than the force up. This tells us the reaction force, which is your apparent weight, will be smaller than your actual weight acting downwards. Therefore, the answer is either B or D, which say the apparent weight is lower than 700 newtons. As the lift is accelerating at a constant rate, the unbalanced force will be constant, and so will your apparent weight. This means our answer is B. Does any of that put you off using a lift? I hope not. If anything, I have found understanding more about something makes me less worried about it. A good lesson for life, perhaps. It doesn't, however, resolve my fears about getting in a lift. Stairs are good for me. This was Think 4. Thanks for watching.